The word thermodynamics stems from Greek words meaning movement of heat, and was developed in the 19th century before the atomic and molecular theory of matter was understood, even before electrons were part of science. So thermodynamics is a macroscopic science relying on mechanical work, pressure, heat, and temperature, and their roles in energy transformations. It was the laws of thermodynamics that dashed the dreams of inventors and industrialists who believed in the possibility of perpetual motion machines. Devices that, upon receiving an initial input of energy, would continue to operate indefinitely without further input. Never happens. We'll briefly cover laws of thermodynamics, which sum up much of what we've explored in previous screencasts. The first law of thermodynamics is a thermal version of the law of energy conservation. It states, heat added to a system equals the gain in internal energy of the system plus work done by the system. The system may be gas in a container, the body of a person or child, or even Earth's entire biosphere. In some applications, work done on or by the system can be neglected. Then heat that is added or taken away equals the gain or loss of internal energy. For example, suppose you put an air-filled, rigid, airtight can on a hot plate and you add heat to the can. The added heat increases the internal energy of the enclosed air, so its temperature rises. If the can is fitted with a movable piston, then the heated air can do mechanical work as it expands and pushes the piston upward. This ability to do mechanical work comes from the energy you put in to begin with. The first law says you don't get energy from nothing. The numbers have to add. The first law of thermodynamics makes good sense. Let's look at piston action in this heat engine, a common four-cycle internal combustion engine. The up and down piston motion rotates a shaft that connects to the vehicle's wheels. First, the intake valve opens and a fuel-air mixture fills the cylinder as the piston is pulled downward. With valves closed, the piston moves upward and compresses the mixture. The spark plug fires, ignites the mixture, which raises it to a high temperature. Expansion pushes the piston downward. That's the power stroke. The burned gases exit the open exhaust valve as the piston moves upward. Then the intake valve opens and the cycle repeats. Shorthand notation of these stages are suck, squeeze, bang, push, and blow. In this heat engine, as with all heat engines, only some of the heat can be transformed to work, with the remaining heat energy expelled in the process. There is always some inefficiency. Yum thermodynamics. The first law has useful applications for meteorologists when analyzing weather. Meteorologists express the first law of thermodynamics in this partial form. Air temperature rises or falls as heat is added or subtracted. Heat can be added to the air by solar radiation, by long-wave Earth radiation, by moisture condensation, or by contact with the warm ground. When heat is added, internal energy and air temperature increase. Common sense. Conversely, air temperature drops when the atmosphere loses heat by radiation to space, when rain evaporates by falling through dry air, or when air makes contact with cold surfaces. Again, common sense. To complete this version of the first law, we add, or when pressure changes. Pressure can do work, which can also change the air's internal energy. Many atmospheric processes involve pressure changes. For processes in which the amount of heat added or subtracted is very small, we can say air temperature rises or falls as pressure increases or decreases. As the volume of air, which we'll call a parcel, rises in air, it gains or loses very little heat, but its internal pressure lessens, allowing it to expand and cool. and do work on its surroundings. The reduced pressure results in reduced temperature. Measurements show that the temperature of a parcel of dry, expanding air can decrease by 10 degrees Celsius for a decrease in pressure that corresponds to a 1 kilometer increase in elevation. So dry air cools 10 degrees Celsius for each kilometer it rises. Thus, if a parcel of dry air at ground level with a comfortable temperature of 25 degrees Celsius were elevated to 4 kilometers, the temperature would be a frigid minus 15 degrees Celsius. Be glad that airplanes are engineered so that you don't notice these changes. The second law of thermodynamics restates what we've learned about the direction of heat flow. Heat never spontaneously flows from a cold object to a hot object. In winter, heat flows from the inside a warm, heated home to the cold air outside. In summer, heat flows from the hot air outside into the cooler interior. The direction of spontaneous heat flow is from hot to cold. The only way that heat can be made to flow the other way, from cooler to warmer, is by doing work on the system or by adding energy from another source, as occurs with heat pumps and air conditioners. Only then can heat flow from cooler to warmer locations. There's a lot of internal energy in the ocean. But that huge amount of internal energy cannot be used to light a single flashlight bulb without external effort. Energy will not of itself flow from the lower temperature ocean to the higher temperature bulb filament. Without external effort, the direction of heat flow is from hot to cold. The third law of thermodynamics states what we've learned about the lowest limit of temperature. No system can have its temperature reduced to absolute zero. As investigators attempt to reach this lowest temperature, it becomes more difficult to get closer to it. Researchers continue to get closer and closer to the elusive absolute zero, never reaching it. There is a zeroth law of thermodynamics, which states that if systems A and B are each in thermal equilibrium with system C, then systems A and B are in thermal equilibrium with each other. Thermal equilibrium means no spontaneous net flow of heat in either direction. We say, two systems, each in thermal equilibrium with a third system, are in equilibrium with each other. The importance of this law was recognized only after the first, second, and third laws had been named. Hence the name zeroth seemed appropriate. I've only touched on the laws of thermodynamics and encourage reading of more on this topic. I want to leave you with a question. First, you can warm your kitchen by leaving a hot oven door open. But can you cool the kitchen by leaving the refrigerator door open? Defend your answer. Until next time, good internal energy.